Hey guys, in this video we're gonna finish chapter 20. So the content of chapter 20.3 and 20.4 will be discussed. So in chapter 20.3 we're gonna look at the relationship between entropy and a new term called free energy. We won't mention work, but if you are interested you can read it through textbook. So in chapter 20.3 we're gonna introduce a new thermodynamic term which is called free energy. Right, so earlier we have entropy, and now we have free energy. Right, so this is the last most important parameter or thermodynamic term that's related to thermodynamics. Right, so the free energy was brought up by an American scientist whose last name is Gibbs. Right, so that's why people also call it Gibbs free energy. Right, so it has this symbol using this capitalized letter G, right, representing his last name. So the reason the free energy was brought up because when we try to determine the spontaneity of a process of a chemical reaction, right? So earlier we had to use the sign of the delta S of the universe, right? So delta S of the universe is the sum of the delta S of the system and the delta S of the surrounding. So we had to measure, right? We had to measure the delta S for the system and the delta S for the surrounding, add them up, and then determine whether this process of this reaction is spontaneous or not, right? So that's actually not preferred, right? So because we have to measure two things. So it would be very useful that to have just one criteria for the spontaneity that we can determine by measure the system only, right? So that's why this free energy was brought up. So based on Gibbs, this free energy is equal to the enthalpy of the system minus the temperature times entropy, right? So here T is temperature in unit of Kelvin, right? So for a process or a chemical reaction, right? So like H and S, we can also measure the change of free energy, right? So if we have chemical reaction, right? So if we know the delta H and the delta S, and we can use this equation, right, to calculate the change of delta G also. Right, so let's see how can we relate this delta G of the system, right? Because we mentioned that we only want to measure this delta G of the system only, right, to determine whether it is spontaneous or not, right? So earlier we have the delta S of the universe, right, equal to the sum of these two. And from the previous video, we know for delta surrounding, right, it is equal to the negative delta H of the system divided by the temperature, right? So we can substitute this delta S surrounding using this term here, right? So that equation becomes this second equation here, right? So if we multiply a negative temperature on both sides, right? So the left side becomes negative temperature times delta S of universe, and the right hand side become delta H of the system minus temperature times the delta S of the system, right? So you see the format of this right hand side, right? So that matches the Gibbs Gibbs equation, right? So matches here, right? So if we want to relate that to the system, right? So we can say we can add the system, right? So this delta H system, which is here, right, minus temperature times delta S of the system, which is here, right? So because of this equation here, so we can say it's equal to delta G of the system, right? So meaning that if we know the temperature and we know the delta H, I mean the corresponding delta H of the and the delta S, we can calculate delta G, right? So also because this term here, this right hand side, is also equal to negative temperature, right, times the delta S of the universe, right? So we can also say this delta G system is also equal to minus T times delta S of universe, right? So basically, because here you have a negative sign, right? So but delta G you don't have a negative sign. So earlier, like we can determine the spontaneity based on the sign of delta S, right? So the opposite will be true for the sign of the delta G. For example, if we want a process to be spontaneous, right, we want the delta S universe greater than 0. But in terms of delta G, because delta G is equal to the negative temperature times delta S universe, right? So for this process to be spontaneous, the delta G will be less than 0, right? For delta S universe, it should be greater than 0, but for delta G, it will be less than 0 for a spontaneous process, right? So on the other hand, for a delta S less than 0, that means the delta G will be greater than 0, right? So that will be for a non-spontaneous process. And then for a equilibrium process, right? So for this process at equilibrium, should say that way. So the delta S is equal to 0, so is delta G. Right. So the chain will be the opposite. Right. So again, for delta first process to be spontaneous, we want the delta S universe greater than 0, but delta G less than 0. Like the other two thermodynamic terms, we can also have a standard state delta G of the system. So here the standard state, right, meaning that all these reactants are at their most stable form, right? So in this way, we can have this node, right, this little circle as a superscript for all the three thermodynamic parameters, right? So using this equation, right? So if we know the standard delta H and delta S for a process or for a chemical reaction, then we can calculate the standard free energy delta G naught. Right, so let's look at this example. Right, so if we have this chemical reaction here, right, so it's a decomposition reaction. So we want to calculate this standard delta G of the system using the given delta H of heat of formation and the entropy, standard molar entropy, right? So these values can be found in the appendix B also, right? So you can see that for the calculations involved in this chapter, right? So this appendix B is going to be very useful. Right, so because this is for all those parameters at 298 Kelvin, right, which is 25 Celsius, right? So if its reaction happens at room temperature, we can just use the value provided in this table. Right, so that's the temperature of this example problem. So because we want to calculate delta G of the system, right? So we need to know the delta H of the system and the delta S of the system. Here, the system refer to this reaction, right? So basically, we want the delta H and the delta S for this chemical reaction, and at standard state, right? So standard state is the most stable form, right? So for delta S, right? For delta H of the system, is basically the sum of the heat of formation for all your products minus the sum of the heat of formation for all your reactants, right? So that's something we learned from chapter 6, right? So for the delta H of this reaction, the reaction is referred to is this system, right? The system referred to this reaction, right? So that they are the same thing, right? So using this appendix B, right, we can find the heat of formation, the delta HF naught, right? So for your products first, right? So you have 3 moles of this KCl 04, right? You multiply 3 by the heat of formation for that compound, right? And then add 1 mole of KCl, right? So you have 1 mole KCl multiply the heat of formation for that compound. So that's all your products, right? For your reactants, you have 4 moles of this KClO3, right? So you have 4 times the heat of formation for that compound, right? So finding those values in appendix B and substitute them in this equation and find that delta H of the system is equal to this number, right? So you notice that the unit is in kilojoule. Right? So for delta S, right? So the same approach, right? Finding the standard molar entropy, right, of these compounds. Again, using the same table, right? So here we use the same approach, right? The sum of all the products minus the sum of all the reactants, right? So finding those values from the table, right? Multiply the corresponding number of moles, which are the coefficients, right? So you got these numbers, right? Notice now you have joule per K, right? So it's no longer kilojoule. So then you can put these two numbers, right, into this equation here. Right? Because you have different unit of energy, you have to do the conversion, right? So in this case, I want to use kilojoule, right? So then I have to convert this joule per K into kilojoule per K, right? So by using this equation, this is the delta H in kilojoule, right? So here we have temperature multiply joule per K, so the K cancel out, right? But you have joule, so you have to convert that into kilojoule, right? So now you get a delta G, the standard delta G of this reaction, right? So it's a negative number which is less than 0, right? So we say it is spontaneous. So the approach to solve for standard delta G of the reaction is one of the two ways to do so, right? So the second way to do so is more straightforward, is using this standard free energy of formation, right? So here we introduce another term related to the free energy is the standard, right, free energy of formation, right? So it's basically the free energy for the heat of formation process, right? So earlier we have this delta H F, right? So that's the change of enthalpy for the formation of this elemental compound or this compound, right? So this delta G F naught is the free energy, right, for this formation process, right? So it's for the same process, but this is the delta F, right? Earlier we learned this is called the heat of formation. Here delta G is the free energy of the formation, and luckily this value at 298 Kelvin is also provided in the same table, also provided in appendix B, right? So in the appendix B, right, you can find the delta H formation, right? So all standard state, right? So delta H F at the standard state, and delta G, right, free energy of formation, and also the molar, right, standard molar entropy, right? So for each species of each compound, right, you can find these three thermodynamic values for this species using the appendix B. So from the example in the previous slides, right, we used the delta H F naught and the S naught, right, to calculate the delta G of the of a reaction, right? So in this second approach, we can just use this delta GF naught, right, to calculate the standard delta G of the reaction, right? So we use this equation. So it's the exact same equation as we use for to calculate the delta H or the delta S of the reaction at standard state. Right, so here all you need to do is find the corresponding delta GF naught for each species in the reaction, right? So you take the sum of the products minus the sum of the reactants, right? So this delta GF and the delta HF work that their properties, right, works in a similar way, right? So for an elemental substance, we said the heat of formation is 0, and that's also true for the free energy of formation, right? So if you have an elemental substance, right, like hydrogen gas, oxygen gas, or like any like a pure metal atom, right? So the delta GF naught will be also equal to 0. And second, a coefficient in the reaction, right, multiplies the delta G by that number, right? So basically, the coefficient in the reaction is the multiplier when you calculate this delta G of the reaction, right? So also, if you reverse the reaction, you have to reverse the sign of this delta G F naught, right? So let's look at the example. Right, so for the same reaction, right? Earlier we use delta HF and the delta HF and the S naught, right? So to calculate this to calculate the delta G naught of this reaction. Right, so now for the same reaction, let's use the second approach. Right, so we use this equation directly. Right, so we can get this individual delta GF naught values using the table in appendix B. Right, so we have 3 moles of this product. Right, so we have 3 times this value that obtained from the appendix B, plus the 1 mole times that. So that's the total of the products, right? Minus 4 times, right? 4 here, right? So 4 times the delta GF naught for the reactant. So at the end, you end up with negative 134 kilojoule, right? So from the previous approach, we have negative 133 point something, right? So they almost give you the same result. When we did the calculation for the previous example problem, I highlighted that the difference of difference in units, right? For delta H is normally in kilojoule, right? On the scale of kilojoule, but for delta S is the unit is joule per Kelvin, right? So the reason is that for most cases, right, the enthalpy change, right, this delta H of a reaction, right, contributes mostly to the delta G of the system, right? So so in terms of their contribution to delta G, right? So delta H contributes much greater than delta S does, right? Based on this unit use, right? So, but remember this delta S has a multiplier, which is the temperature, right? So when we want to determine whether the delta G is greater or less than 0, right? So we need to compare, right, the value, the magnitude of delta H, and also this term, the temperature times delta S, right? So that's why the temperature, right, for a lot of reactions will be an important factor to determine whether it's spontaneous or not, right? So based on the sign of delta G, we can determine whether it's spontaneous or not, right? So that delta G is depends on the delta H and the T times delta S, right? So in this case, in order to determine the sign of delta G, we have 4 scenarios, right, in terms of the sign of delta H and the delta S, right? Because for delta H, we could have a positive or negative, and for delta S, we could also have a positive and negative, right? So there are 2 times 2, 4 combinations, right, in terms of their sign, right? So first, when you have a negative delta H and a positive delta S, that makes delta G to be negative no matter what temperature it is, right? Because delta H is negative here, and U minus a temperature is positive, right? Temperature here is greater or equal to 0 Kelvin, right? So normally it's greater than 0, right? So 0 is the absolute 0 temperature. So if your delta S is positive, you minus a positive number, right? So negative T times delta S will be also negative, right? So which is here, right? So you have a negative number, right? And then add another negative number here. So that will make delta G less than 0. So no matter what temperature it is, the delta G will be less than 0, right, at all temperatures. So it is spontaneous no matter what temperature it is. But on the other side, if you have a positive delta G and a negative delta S, that will make delta G greater than 0 all the time, right? Because you have a positive number and then adding another positive number, right? So it will be positive all the way, delta G here, right? So it is non-spontaneous at all temperature, right? So if you have both positive or both negative, then you have to determine the relative magnitude of these 2 terms, right? So you have to determine whether the sum of these 2 terms is greater than 0 or less than 0, right? So then this reaction will depends on temperature, right? If you want to determine whether it's a spontaneous or not. So the temperature will play an important role here. So the magnitude of this native T times delta S, right, will depends on the temperature, right? The higher the temperature, the higher the magnitude of this term here, right? So for a when they are both positive, right? So that means your delta H is positive. So you want this term here, right, minus T delta S to be very negative, right? So you want this temperature to be high, right? So this term is negative enough, right? So that's why overall delta G will be negative, right? So in this case, only higher temperature, right, give you a negative delta G, right? So if it's temperature is low, right, so is the term negative T delta S is not like big enough, right, to make the overall delta G be less than 0, right? So in this case, the delta G will be greater than 0, right? So if you have a reaction with delta H and delta S be negative, right? So they're both negative, the trend will be opposite, right? So for this reaction to be spontaneous, you want it to be at low temperature, right? So you want it to be at low temperature, because if it's temperature too high, the negative T delta S double negative will make it positive, right? So higher temperature means a greater or more positive term, right? So that will make the overall delta G greater than 0, right? So in this here, the higher temperature will make delta G greater than 0, right? So this is a very useful table here, right? So when you see a problem asking you whether it's spontaneous or not, right? So refer to this table, right? So if it belongs to the first two scenario, you don't have to calculate it, right? You can just tell based on the sign of delta H and the delta S, right? So this you don't need calculation. But if they're both positive and both negative, then you have to do the calculation and determine whether it's spontaneous or not. So let's work on an example problem. Okay? So you have a sulfur dioxide reacting with oxygen to get sulfur trioxide. So in this problem, it tells you the temperature is at 298. Right? So again, remember our good friend, the table in the appendix B. Right? So all the values we need is in there. Right? So it tells us for this reaction, right? The delta G is given, delta H is given, and the delta S is given. Right, so we want to first calculate the whether this reaction is spontaneous at 25 Celsius, which is 298 Kelvin. Right, so this is already 298 Kelvin. Right, so there's no change in temperature, and also predict how delta G will change with increasing temperature. Right, so pause the video and try to work on it by yourself. Right, you can go to the previous slides, right, to learn this again, right, so to help you solve this problem. Right, so again, right, so to determine whether it's spontaneous or not, you can just calculate the sign, right, the sign of the delta G, right? So in this case, the delta G is already given, right? So it is negative, right? So we know at 298 Kelvin it is spontaneous, right? So how does it change with an increasing temperature, right? So you can refer to the table in the previous slides, right? So you have a negative delta H and a negative delta S, right? So they're both negative, right? So when they are both negative, right? So when delta H is negative and when also delta S is negative, remember a higher temperature will make the delta G more positive, right? So will be make it less negative or more positive, right? So you can also figure that out by just putting the number in here, right? So substitute some temperatures in there and see the change, right? But from the previous table, we know that when they're both negative, right? So an increasing temperature, right? So that will make delta G more positive, right? So delta G will become less negative or more positive at higher temperature, right? So we will become less spontaneous and eventually become non-spontaneous. And for part B, assume that this delta H and delta S are constant with T, right? So meaning that when you change the temperature, these two values doesn't change, right? Remain as a constant. So I ask you, is this reaction spontaneous at 900 Celsius, right? So again, pause the video to try to solve this by yourself, or just use this equation. So it's pretty straightforward, right? First, I will convert Celsius into Kelvin, right? So that's the temperature in Kelvin. So I use this equation directly. So delta H is given, right? It is in kilojoule. Delta S is given here, but it's in joule. So you have to convert that into kilojoule. Multiply the temperature in Kelvin, right? So here this is the temperature in Kelvin. You do the calculation, you find out this is 22 kilojoule, right? So it's much greater than 0. So in this case, the reaction is no longer spontaneous. So as you just see, right? So if the delta S and the delta H of a reaction have the same sign, right? When they're both positive or both negative, right? A reaction can be spontaneous or non-spontaneous, right? Depends on the temperature, right? So based on that, we can actually calculate the temperature at which this reaction become spontaneous or non-spontaneous, right? So because we know that this reaction is at equilibrium when the delta G is equal to 0, right? So that's the turning point, right? So of spontaneous and non-spontaneous, right? So when at equilibrium, you have delta H minus T times delta S equal to 0, which is equal to delta G, right? So meaning that this delta H here is equal to temperature times delta S, right? To find the temperature for this to happen, we just need to move delta S to the left hand side, right? So we have temperature equal to delta H divided by delta S, right? So that means if delta H and the delta S, they have the same sign, right? So they have the same sign, right? So both positive or both negative, we can calculate the temperature at which this reaction become spontaneous or not, right? Using this equation, right? So for example, when we look at this chemical reaction, right? So copper 1 oxide react with carbon, I give you elemental copper and carbon monoxide, right? So we want to know at what temperature this reaction is gonna become spontaneous, right? So the delta S is given, delta H is given, and they're both greater than 0, right? So then they have the same sign, right? So we have to use this equation, right? So again, I will convert the unit of energy, right? So you have to match them. So in this example, we convert the kilojoule from delta H into joule, right? Divided by delta S. So you have 352 Kelvin, right? So meaning that this reaction, right? So because they are both positive, right? So when they're both positive, that means the reaction will become more spontaneous when the temperature increases, right? So that means if the temperature is less than this, right? So when the temperature is less than this 352 Kelvin, it is non-spontaneous, right? But if it's greater than 352, right, it will be spontaneous, right? So this is true when they're both positive, but if they're both negative, you can still use this equation, but after you get the temperature when the temperature is greater than your resulting temperature, will be non-spontaneous, right? So the trend will be opposite. So in this figure, right, you can also see, right, so here you have a temperature, right? So when the temperature is below this 352 here, right, the reaction is non-spontaneous, right? And after this temperature, the reaction become spontaneous. Right, so in this example, again, let's look at this reaction in the previous example problem. Right, it's basically how do you get elemental copper, right, from a compound. Right, so have you wondering why we need to add carbon? Right, can we just use the first equation here, right? So like copper oxide, let it decompose by itself and give you copper and oxygen. Right, so why do we need to add carbon, right? Because this reaction, the first reaction, is also possible. And that the reason is that, right, looking at the sign, right, so looking at the sign of delta G, right, so even at 375 Kelvin, right, so earlier we determined that for this reaction to be spontaneous, we need a temperature of 352 Kelvin, right? So when the temperature is higher than this, and when delta H and delta S and are both positive, right, we say higher temperature we become more spontaneous, right? So if it's at 375, right, greater than this temperature, this reaction will become spontaneous, right? You see this delta G is less than 0, right? So the reason we want to add carbon is that for this reaction, right, that if you let it decompose by itself, even at this temperature 375 Kelvin, the delta G is so positive, right? So it's so positive, it's not spontaneous, right? So but at this temperature, when carbon react with oxygen and generate this carbon monoxide, it is a very spontaneous process with a very negative delta G value, right? So this magnitude is even, right, greater than this first reaction here, right? So that's why if we combine this first and the second reaction here, which is our target reaction here, right? So if we add 1 and 2, right, we got the reaction at the bottom, right? So this is called the coupling of reaction, right? So if we add this 2, we can get this equation. So we have 140 from reaction 1, right? So plus the delta G from reaction 2, which is negative 143.8, right? So overall, you have a negative 3.8, right? So you have a negative 3.8 kilojoule, right? So that's why we want to add carbon, right, to produce this elemental copper. But let it react by itself, right? The delta G too positive, right? It's not preferred, right? So adding carbon will help, right, for this reaction to proceed or to be spontaneous. Actually, a lot of important steps in organisms or in like human lives, right? So a lot of important chemical reactions or biological process, right? Those processes are non-spontaneous, but it's coupled with other process that will trigger, right, this non-spontaneous process. Right, so this concept of coupling reactions actually the key of life actually. Right, so basically a good example is that let's not talk about human body or organisms. Let's say if you want to start a car, right? So you want to start a car, right? So you know that burning the fuel, right, will make the car move, right? So but how do you burn the fuel? You have to like couple it, right? You have to couple it with a start engine process. You need to give some sparkle, right, at the beginning, right? So if you combine these two, you can make a car work, right? So without starter engine or give that initial spark, you cannot start the car. So for homework in chapter 20.3, there are three problems. Right? So for 20.51, 20.53, right? So there are three reactions. So you only need to work on reaction 1. Right? So for 20.61, the chemical reaction is now given. Right? So I'm giving you the reaction here. So you can use this reaction for this problem. The last part of chapter 20 is relating the free energy delta G, right, and under equilibrium of a chemical process. Right, so again, that's another way to determine the direction, right, of the chemical reaction. So earlier we determined the direction based comparing Q and K. Right, so in this chapter 20.4, we'll also do so by using the free energy, right? By calculating the free energy. So in chapter 20.3, we learned that for the delta G, for the free energy of the reaction, right, the change of free energy, if it's greater than 0, right, we said it is non-spontaneous. If it's less than 0, we said it is spontaneous. Right, so the spontaneous is in terms of a chemical reaction. For example, if you have a chemical reaction A to B, right? Let's say it's a reversible reaction, right? Why is the spontaneous in terms of A, right? Because A is your reactant and the B is your product, right? So you're talking about reacting A and forming B, right? So meaning that this is referred to A, right, to your reactant. Right, so from the previous chapter, we know that this reaction will proceed to the right if Q is less than K. Right, so that's what we learned before. And the reaction will proceed to the left if Q is greater than K. And if they're equal, is at equilibrium. Right, so in terms of delta G, right, so if it's less than 0, that means from A to B is spontaneous. Right, so that's we say if delta G is less than 0, right, so we say it is spontaneous to the right, right, because we write the reaction in this way, right, from A and generating B. Right, so on the other end, if this delta G is greater than 0, A to B is not spontaneous anymore, but B to A will be spontaneous. Right, so that's we say this spontaneous reaction will prefer to the left, right? The direction will be to the left. Right, so here you have to be careful, right? Which one you're talking about, right? So from A to B, right? If it's less than 0, it is preferred, right? But if it's greater than 0, A to B is not spontaneous, but B to A will be spontaneous. Right? So again, if delta G is equal to 0, right, it is at equilibrium. Right, so now you can see that we can not only compare Q and K, right? So we can also calculate or determine spontaneity based on the sign of delta G, right? So we can relate these two terms, right? So using the term that delta G, right, is actually equal to RT times the natural log of the ratio of Q over K, right? So here the delta G is involved and the ratio of Q over K, right? So when we compare Q over K, there's a ratio here, right? So if we take the natural log of it, right? So that will also be a part of the reaction, right? So now you have R and T, those are constant, right? T is the temperature in Kelvin, right? R is the universal constant, right? 8.314. Unit is Joule per mole times Kelvin. Right, so for natural log Q minus K, you can rewrite it as natural log Q minus natural log of K. Right, so when you have natural log of A divided by B is equal to natural log of A minus natural log of B. Right, so here you have a RT in the front, right? So this equation is equal to RT times natural log Q minus RT times natural log K. Right, so when you have a Q and a K that are very different, right? So when the Q and the K are very different, that means that these two terms, the value of these two terms are also very different. So the delta G will be very positive or very negative, right? So that means the reaction will release or absorb a lot of energy, right? Due to this big difference of Q and K. But if they are similar, right? So when they're similar, that means they're very close. The reaction is very close to equilibrium, right? So that means the reaction is almost, right, reach completion. So the reaction release or absorb very little amount of energy, right? So from the previous slides, we can see the relationship between the delta G, right, and the equilibrium constant using the equation. Right? So here you see how this equilibrium constant and the delta G is actually related, right? So if it is system is at standard state, right? Standard state meaning that we have 1 mole of for the gases is 1 atm, and for the chemical solution it has 1 molar, right? So that's the definition for standard state, right? So if at standard state, the Q here, remember Q is the reaction quotient, right? So everything, all the activity for the reactants and the products will be 1, right? So overall, this Q value will be equal to 1 because that's based on the definition of the standard states, right? So you have 1 for everything. So the ratio will be also equal to 1. So when this Q is equal to 1, right? So this natural log 1 is actually here is equal to 0. Natural log of 1 equal to 0. So RT times 0 is equal to 0. So this term is actually eliminated. So what you have left is this standard delta G is actually equal to negative RT times natural log of equilibrium constant, right? So now you can see that if the system is at standard state, right? So if we know the standard free energy, right? If we know the standard free energy, we can calculate equilibrium constant at a given temperature, right? Because R is given, right? So for example, in this example, we have this chemical reaction, right? So they are gas phases, and the temperature is at 293, right? So again, we can use our appendix B, right? So this is our good friend for chapter 20. So if we know the delta G, right, for this reaction, we can calculate the equilibrium constant, right? So the first thing we need to do is find the delta G, standard delta G for this reaction, right? Because T is given, right? R is a constant, right? So the only unknown will be the equilibrium constant. Remember, there are two ways, right? In chapter 20.3, there are two ways to calculate this standard delta G, right? So we can either use the delta G of formation, right? Standard delta G of formation, all right? That's the first approach. Right? Second approach is using the combining the delta H of formation and the standard molar entropy, right? So we need to use both of them, right? So apparently this way is easier, right? Because all these numbers are given in the appendix, so I will use this delta GF naught, right? So you can find the corresponding values for these three substances, right? So using the table, find this one, find this one, and find this one, right? So we can do the calculation, and then the delta G is negative 36 kilojoule, which is less than 0, right? So it is a spontaneous reaction, right? So how about is a what is equilibrium constant K, right? So using this equation, now we got the delta G, right? So we can plug that in here, and the temperature is given, R is a constant, right? So to solve for K, first we can divide minus RT on both sides, right? So on the right hand side you have natural log for K left, and on this side you have negative delta G divided by RT, right? So you have this all the numbers you need are given or being calculated, So the natural log of k here is equal to 14.53. Right? To get the k, you take the e to the exponent, right, on both sides. Right? So you make both sides as the exponent to e. So on the left hand side, you have e to the natural log of k, which is basically equal to k. So that will equal to k. Right? So on the right hand side, you have e to this ratio here, 14.53. Right? So k will be 2 times 10 to the 10 to the 6. Right? So it's a very large equilibrium constant number, right? So we know when we have a large k value, that means this direction is preferred to proceed to the right, right? So that's why it's delta G is very negative, right? So it's spontaneous to the right hand side. So in this table here, right, you can see how the equilibrium constant k changes with the delta G value, right? So based on the equation we used in the previous couple of slides, right, says delta G equal to negative RT times a natural log of K, right? Because you have this negative sign here, right? So the greater the, like when this K value increases, right? So this delta G become more negative because of this negative sign, right? So what does this tell you, right? So what does this tell you? That means that when you have a equilibrium constant that is very large, right, that means the reaction is right spontaneous to the right hand side, right? So that means the reaction is preferred, right? That means k is k is the equilibrium constant, right? The concentration terms of the product divided by the concentration terms of your reactants, right? So that means, right, so this ratio is big, right? So that means the reaction is preferred to the right hand side, right? So that means it's spontaneous, right, to the right, right? So that, and then that's also corresponds to a very negative delta G value, right? So the more negative the delta G is, the more spontaneous it is to the right hand side, right? So next time when you look at a problem, right, so if you the delta G, standard delta G is given, or the equilibrium constant given, right, you can basically tell whether this reaction is spontaneous or not. So earlier we look at the standard state, right, when we want to correlate the delta G and this equilibrium constant, right? So what if it is not at the standard state, right? So if it's not at standard state, can we find the free energy change, right? So the answer is yes, right? So even not at the standard state, right? So we can also find the delta G of a reaction, right? So in this case, you can no longer, right, eliminate this term, right? Because Q is no longer, right, equal to 0, right? So it could be any concentration of reactant and the product. For example, when you just mix two reactants, right, without any product, right, so this you can no longer ignore the Q here, and because it's not at equilibrium at all, right? So in this case, but when you look at this term, right, so in the previous slides, right, we said this negative RT natural log K is equal to standard delta G, right? So if you replace this term using this standard delta G, right, so you can rewrite this combination here, right? So we can replace this negative RT natural log of K using standard delta G, right? So this equation become delta G equal to standard, right? So delta G equals standard delta G, right, which is this term, and the plus RT natural log of Q, right? So RT natural log of Q. So standard delta G, right, again we can calculate it, right, using appendix B, right? So we can find it from appendix B. So RT, right, if we know the temperature, right, and if we know all the concentrations in your chemical reaction, we can calculate this Q, right? So we can calculate the delta G, right? So remember, at standard states, right? So this Q equal to 0, your delta G is equal to delta G naught, right? So again, this is very important, right? So at standard state, right? So this delta G here is at standard state delta G, right? Based on definition, and that's because the natural log of Q is equal to 0, right? So that cancel out this term here. So your delta G equal to delta G naught. But at any other conditions, right? So you have to use this equation, right, to find out the delta G. Right, so let's work on an example problem, right? So kind of like go through this important relationship between the equilibrium constant and the delta G, or the standard delta G. Right, so we look at this equation before, right? Sulfur dioxide reacting with oxygen gave you sulfur trioxide. So this problem has three questions, right? So A, we want to calculate the equilibrium constant at 298 Kelvin, and the delta G at that temperature is already given, right? So we apply this equation directly, right? Again, we to rewrite this reaction, right? So we divide minus RT on both sides, and then we have delta G naught, right, divided by minus RT, and on the right hand side we have natural log of K, and then we use this term as the exponent for E, right? So we have E to this entire term on the left hand side, right, which is this, right? So on the right hand side you have E to the natural log of K, which is equal to K, right? So to calculate K, you just need to calculate this term, right? So everything in this term is given, right? All these values are given. Remember the unit, right? You have to match the unit. So at the end you have this very large equilibrium constant value, right? So it is right, so a very spontaneous reaction, right? You can also know that by this large negative number here for delta G. So for question B, it gave us a certain concentration for these gases, and it asks us in which direction the reaction will proceed to reach equilibrium, right? So in this case, we can compare Q and K, right? So notice the number given here is in ATM, and I told you guys, right, when you calculate the Q involving all gases or involving any gases, use the number of ATM directly as the concentration, right? So now you can just apply the number in ATM directly into this to calculate this Q. And also remember here, right, the exponent is the coefficient, right? Don't forget about that. So you have the Q, right, equal to 4 here, but this Q here is way less than the K, right? K we calculated earlier is a very large number, right? So this Q is much smaller than K. So we say the reaction will proceed to the right, right? It will be spontaneous to the right. So the last question, they want us to calculate the delta G for that system in part B. In part B, we have a certain numbers, I mean the certain concentration of each of this substance in this reaction, right? So we determine Q was like equal to 4, right, which is much less than K, so the reaction proceeds to the right, right? So basically in this problem C, we want to know what does this delta G, right? What's the delta G correspond to a value of Q equal to 4, right? So apply this equation directly, right? So delta G naught is something given in part 1, right? So the value is already given, and for RT natural log Q, we know R, we know T, and the Q equal to 4, right? We calculate that from part B, right? So here only thing to need to pay attention is that delta G naught is in unit of kilojoule, right? So here your R constant contains joule, not kilojoule, so you have to convert it, right? So at the end you got negative 138.2 kilojoule per mole, right? So meaning that at standard state, right, when all the concentrations of these gases, right, say at standard state, right, so the concentration for everything is in this reaction is equal to 180 m, right, 1 equal m for everything. The Q is equal to 1, right? In that case, the delta G is equal to delta G naught, right, which is equal to this given value, negative 141.6 kilojoule per mole. Right, so that's at standard state. Right, so in part B, you have a certain concentration of each of these gas. Right, so that's no longer at standard state. Right, so now if you don't have a standard state, right, so you have various concentrations of each reactant and the product. Right, that case Q is no longer equal to 1. Right, so that means your delta G is no longer equal to delta G naught, right? Your delta G will be equal to delta G naught plus RT times natural log of Q, and then the Q is calculated, right, based on the given concentrations for your reactants and the products. Right, so for this problem, right, so when the concentration of each gas were given, right, as given in part B, right, so when you have, that means when you have a Q value equal to 4, the corresponding delta G, right, which is no longer equal to delta G naught, right, that will be equal to 138, right, so it's slightly different than the standard delta G naught, but it's still very negative, right, meaning that it is still very spontaneous, right, to the right hand, to the direction of the products. But as you can predict, right, that if this Q value is even greater, right, so this is greater, say, way more or close to the K value, right, so that will make this term here very positive. So when it is close to the magnitude of delta G naught, your delta G will be close to 0. And in that case, the reaction will become less spontaneous. Right? And when this Q is equal to K, this RT natural log of K will be equal to negative delta G. Right? So when this Q is equal to K, this RT natural log of Q will be equal to negative delta G naught, right? So you add, they will be equal to 0, right? So delta G will be equal to 0. So consider all the chemical reactions based on their K value or how negative the standard delta G value is, right? We can divide the chemical reactions into two categories. So first called the product favored reaction, and the second is called a reactant favored reaction. Right, so for the one on the left, right, product favored, right, as we conclude from our example problems, we want a K, right? We want a very large K value. We want a very high K value, or we want this delta G naught, right, with a very negative number, right? It's very less than 0. So in that case, right, if we're talking about a reaction from A to B, right, it's a reversal reaction. If you have a large K value or delta G naught way less than 0, that means the reaction, right, will proceed to the right, and that's why we call it product favored, right? It's the product favored. And to read this figure, right, so say if you right, follow this A to B, right, from A generating B. That means when you have pure A generating pure B, right? So any point in the middle here will be a mixture of both, right? But the closer to the right hand side, that means the more product has been generated, right? So from the beginning, if you follow this green curve, right, for A, the free energy is decreasing, right? It's decreasing. So your delta G, right? So final is smaller, right? So delta G is less than 0, right? So from the initial pure A all the way to the equilibrium point, right? You have a delta G, right, less than 0, right? So product favor doesn't mean that the other direction is impossible, right? So the other direction is also impossible, but less favored, right? So this region on the right hand side, right, so indicate that if you go beyond this equilibrium position, right, so the direction here, the green curve will go back, right? So when they go back, right, so if you keep going, right, if you keep going from this point, right, to the pure B, right, if you keep going, you the G value, right, it actually increases, right? So your delta G will be greater than 0 now. So that will shift the equilibrium back to the equilibrium position, right? So the direction will proceed to the left. So similarly, right, for reactant favored reaction, the everything will be the opposite, right? So if you look at this curve here, so here you have from pure C to pure D, right? So from C generating D, right? But in this case, if you proceed from left to right, you see the G value actually increases. So your delta G is actually greater than 0. That is not spontaneous, right? So meaning from C to D is not preferred. But if you go from D to C, right? If you go from D to C, the G value decreases, right? So G value decreases. So delta G will be less than 0, right? So that means if you go from right to left, which is D to C, right? So the direction will be spontaneous. So that's why it's called reactant favored, right? Because in this case, C is your reactant. So for homework, we have 3 problems. 20.67 only do equation B, 20.73 and 20.79. So these problems are related to the relationship between K and delta G naught, and also calculate delta G, right, based on the Q value. Right, so the next video will be posted next week, and that will be the final chapter, which is related to the electrochemistry.